Now let's see how we can implement a union that utilizes an enum tag to manage multiple user statuses efficiently. In this code, we start by defining a status tag enum that describes three potential states for a user profile: active, inactive, and deleted. This enum serves as a clear identifier for the state of the union, enhancing code readability. Next, we create the user status union, which leverages the status tag enum as its tag. Here we specify that when the user is active, a Boolean value is stored. When inactive, a floating point number representing the duration of inactivity is held. And for deleted users, there is no value at all, void. This structure promotes clarity. By looking at the user status union, developers can immediately understand what each state represents. Another invaluable aspect of our implementation is the method encapsulation within the union. By integrating behavior directly into the union, we promote a cohesive structure where data and its associated operations are bundled together. This not only organizes our code, but also prevents potential errors by ensuring that state management occurs within defined methods. Now let's take a look at how we can implement user status management using the checkUserStatus function, which effectively utilizes a tagged union. This function takes a user status union as input and employs a switch statement to evaluate the active state of the user. Depending on the user's status, active, inactive, or deleted, the function executes different behaviors. For active users, it displays a simple message confirming their status. In the case of inactive users, the function prints out the number of days they have been inactive, enhancing user engagement by providing context. Lastly, for deleted users, the function outputs a message indicating that the account has been removed. This approach not only maintains code clarity by leveraging the enum tags for state management, but also strengthens type safety. By conducting a thorough evaluation of the union's value, the compiler ensures that you are accessing valid fields associated with each state, which minimizes the risk of errors. With this structure, each branch clearly represents its logic, making it easier to understand and maintain as your application evolves. Now let's take a look at how to integrate methods directly into our user union. This is where the power of encapsulation truly comes to life as we create an update method that modifies the internal state of the union based on incoming parameters. We define a function called update, which accepts a mutable reference to the user union and a new status, allowing it to update the user's state seamlessly. Inside the update method, we use a switch statement to determine the type of the new status. Depending on whether it is active, inactive, or deleted, we appropriately assign the new state to the union's active field. This structure ensures that we can manage user states in a clean and organized way, centralizing state transition logic within the method rather than scattering it throughout the codebase. By leveraging this method, we simplify the process of state updates, making it clear how transitions occur. This approach not only keeps the code modular but also adheres to object-oriented principles, enhancing readability and maintainability. The encapsulation of behavior within the union aligns data closely with its functionality, which is a cornerstone of effective programming practice. Now let's implement an example that demonstrates the practical usage of our update method to manage a user's status. In this test scenario, we initiate a variable user status set to user active, indicating that the user is currently active. This structure allows us to hold different data types based on the user's status, ensuring type safety through the use of our defined union. Next, we invoke the update method to change the user's status to user inactive, passing a floating point value representing the duration of inactivity. This showcases how the method smoothly transitions the user's state while keeping the code clear and organized. Following this update, we utilize the checkUserStatus function to verify that the status change has taken effect, displaying relevant information about the user's current status. Finally, we demonstrate another status transition by marking the user as user deleted. Again, we call checkUserStatus to confirm that the status update was successful, which should yield a message indicating that the user account has been deleted. Through this process, we can see how the update function effectively manages transitions between various user states, enhancing maintainability and comprehension in our codebase. Now let's take a look at how we can implement a method within our tagged union, user, to provide dynamic status messages based on the current state of a user. The status message method is defined as a member of the user union, enabling it to return a descriptive message depending on whether the user is active, inactive, or deleted. When the method is called, it employs a switch statement to evaluate the current status of the union. If the user is marked as active, the method returns a string indicating that the user is active. Similarly, if the user is inactive, the message reflects that status, providing clarity about the user's inactivity. Lastly, when the user account is marked as deleted, the method returns a specific message signifying that the account has been removed. This encapsulation of behavior allows methods to leverage the underlying data in a structured way, enhancing the readability and maintainability of the code. By consolidating status-related logic within the union, we create a cohesive structure that simplifies user state management while providing meaningful feedback to the program's users. Now let's take a look at how we can implement a test to retrieve user status messages using our user union. The test begins by initializing user status to the active state, signified by user, active true. This sets the user status to active and allows us to call the status message method, which provides a human-readable message reflecting the current status. By utilizing the std debug print function, we output this message, which informs us that the user is active. Next, we simulate a status update by changing the user state to inactive with a duration of 3 days using the update method. Again, we call status message to display the updated message, which indicates the user has been inactive for a specified duration. Finally, we transition the user's status to deleted by invoking user status. Update user, deleted void. The last call to status message confirms that the user account has been marked as deleted. Through this code, we can see how the dynamic nature of the union's methods can provide meaningful feedback based on the user's current state, showcasing the seamless integration of enums and methods for effective state management. Creating unions that can infer enum tag types and contain methods enables a level of elegance and simplicity in how you manage states and behaviors in your code. By adopting these practices, you not only maintain memory efficiency, but also enhance the readability and maintainability of your codebase. Incorporating enums as tags and methods within unions allows you to encapsulate logic neatly and fosters an object-oriented approach in a procedural programming context. This synergy of methods and data structures creates more intuitive interfaces, making it easier for others who come across your code to understand its intention and functionality. In summary, we've explored the advanced features of unions, such as inferring enum tag types for state management and encapsulating methods for behavior. By adopting these techniques, you can create flexible, clear, and maintainable code that adapts easily to changing requirements while maximizing efficiency. Union types allow you to design complex systems without sacrificing code quality, making your programming endeavors not just productive but enjoyable as well.